lecture.
Hello everyone. Welcome to the Math Methods 3-4 lectures. So this is presented by ATAR Notes, as you guys already know. Some other sort of resources ATAR Notes offers apart from these lectures are study notes, newsletters, articles, etc. to really help you guys get that boost on your studies. So definitely check those stuff out. We also have other resources like study guides and tutoring as well. All right, so without further ado, let's get started. So my name's AJ. I graduated in 2021, so like 2-ish years ago, which feels like a while. And yeah, I currently study neuroscience and genetics at the Australian National University. I don't think I wrote my email on here, so I'll quickly do that. So my email is aj@cutesmart.com. So if anyone has any questions about, like the things I study as well, and alongside obviously like the methods questions, feel free to shoot me an email. But yeah, I'm more than happy to give advice on moving interstate because I grew up in Melbourne and then moved to Canberra for university. So if anyone is thinking of moving interstate, feel free to shoot me an email to talk about that. And also obviously feel free to shoot me an email about any methods questions. And you're like making bound references, studies, all of that in general. Also feel free to drop questions in chat while you're watching. I'll be lurking in chat and answering any questions that pop up. Before we get started into the content stuff, I would like to suggest that if you see a question that's already been asked, try not to ask it again, just because if duplicates come in, I'll only be answering one of them. There might be an upvote function. If there is an upvote function and you see a question you like, just press upvote. It'll probably go to the top of the list and I'll see that. But yeah, so hopefully you guys find today useful. You should be able to access the slides. I've changed the order a little bit, but it's all about this. It's more or less the same. In some, in the chance that we don't get through the final remaining stuff, most of these notes are quite detailed. So have a read through them as well. And a lot of this can be put in your bound reference, and I'll talk about the bound reference a little bit at the end as well. Okay. An overview of what we're covering today. We're going to be doing, first, we're going to talk about integration and antiderivatives. Sort of my favorite part of Unit 4, sort of finishes off calculus. Then we're going to start talking about probability. So I'll do a little bit of an introduction to probability. So I'll talk about some of the prerequisite knowledge you guys sort of need for the upcoming stuff. You guys would be familiar with a lot of the prerequisite stuff. Definitely would have covered it in year 10 and year 11. And then after that, we're going to be talking about discrete probability, and then an extension of discrete probability known as binomial distributions. Then we're going to sort of finish up with continuous and normal probability, or normal distributions. All right, let's get started with integration. So integration, or taking an antiderivative, is the opposite to doing a derivative. So if I have some derivative function here, right, so you can see that it's like df of x with respect to dx, right? That's taking the derivative of the function f of x with respect to dx. If I want to reverse that and find the original function, f of x, I can do this operation known as an integral, right? And a lot of you would have already been, would have encountered this maybe in Unit 1 and 2, and probably as like from school as well, hopefully. If not, that's all good. It's always good to get a head start on your school. So the integral will always spit out the original function that was like derived, I guess, initially. So it'll spit out f of x. And another thing you always need to write with an integral is this plus c. So a lot of you know that when you take a derivative, right? So if I take the derivative of a constant value, maybe something like 4, right? 4 is constant. It doesn't change with any variable. That's going to be equal to 0, right? And so if I have a function like x squared plus 2, if I take the derivative of this function, right, I'll get 2x. That plus 2 is just gone. So if I'm integrating 2x with respect to dx, sure, I'll get the x squared part, right? But I won't get the 2 because in my mind, that 2 just doesn't exist, right, when I'm doing the integral. So to sort of cover for that, we write a plus c. And our plus c is any real number, more or less, right? And sometimes they'll give you enough information to solve for what c is, right? So maybe they'll tell you that it goes through the point 0, 2, and using that, you can work out what plus c is, right? But yeah, make sure you include that. Usually you'll lose marks if you don't. There is one case where you won't, and sometimes it'll ask for like, oh, that's too many n's. They'll ask for like an antiderivative or an integral of something, and that just is one solution, right? So adding the plus c gives you, like, shows you that it's a family of functions. There's multiple solutions. If you don't include the plus c, you're only saying that's the one solution there is to that integral, right? Another thing to not forget is the dx. So what that says is that when you take this integral, you're doing it with respect to x, right? The change that you're trying to reverse is that change that's being done to x, right? Maybe you'll be sometimes, if you guys are doing like sort of those physics application questions, you'll be dealing with functions that are with respect to time. So when you integrate that, you need to change that to dt, right? So make sure that d whatever at the end is consistent with the actual variable you're integrating, right? Otherwise, you will lose marks. In some questions, you'll see that the antiderivative is represented by a capital F of x, and that just generally like refers to the original function or the function that's being anti-derived. Usually, the question will just tell you because they don't want to confuse you with random stuff like that. Cool. Let's go through some integration rules, and then maybe we'll have a crack at doing a practice question. Okay, so some rules with integration is that if I'm taking an integral and I'm multiplying it by some constant, which is represented by k in this case, that constant can just be dragged out to the front. So what do I mean by that? If I've got the integral of 5 of f of x doesn't really matter what it is. It could be x squared, right? That's the same as taking the integral of 5 times the integral of f of x with respect to dx, with respect to x, sorry. So it's a relatively straightforward rule, but it can save you a little bit of a headache when you're trying to integrate something or you're trying to change an integral to make it fit a rule. So that is quite useful to know. So yeah, make sure this is a rule that you guys are really familiar with. It should be in your like formula sheet that they give you, but I think this is a relatively simple rule to remember. So I hope you guys all remember this one here. Another one that I think is a little bit more tricky to understand, but is probably more important than the last, in the sense that it's quite particular to some question types, but it is sort of those high yield topics where often they'll ask you like a lot of questions from that same bit. So splitting up terminals. So we'll talk a little bit more about definite integrals in a little bit, but basically the fundamental theorem of calculus, right, is that if we have a definite integral, right, like so, what that means is that we find the original function, represented by capital F, and then we sub in the values of the terminal, and then we subtract them, like so, right? What splitting up the terminal says is that, let's say I have some function, right, that looks a bit like this, right? If I want to take the integral from a to b, right, and I, have some third point I know as well, maybe some point c, right, I can take the integral from a to c, which is represented by this, and then add that to the integral of c to b, which was represented by this. And you can see from the shaded area that I've shaded in, that still represents the total like span of that integral, the total area represented there. We'll talk a little bit more about area under the curve as well when we talk a little bit more about definite integrals. So if you're a little bit lost on this part, don't worry too much. Just know that you can split up definite integral terminals like so. So I'll sort of touch on this again when we do a definite integral question. Okay. Another thing we can do is that if we have two functions that are being added, it's really important that they're being added. If they're being multiplied, you can't do this. If they're being added, you can just split them up into two different integrals like so. So sometimes it can make, if you see a function like this and you get like pretty confused and you don't know how to integrate it all in one go, that's all good. Or maybe you're just double checking your answer. It's perfectly fine to just split it up into two integrals like this. Right? What's not fine is having an integral like this, right? And splitting that up into something like this, right? Like this doesn't work. Sorry, my integrals are a little bit wonky today, but hopefully you guys, this wasn't a horrible integral, but whatever. Oh, I just realized the camera cuts that off. That's my bad. I'll rewrite it again. So what you can't do is this, right? So if you have the integral of x cubed dx, you can't split that up into this. And so just keep that in mind when you're sort of doing this rule. I see a lot of students get confused with this. Also, when you do split it up, one thing to note is that these terminals remain the same, right? You're still integrating over, that terminal, but you can also do it with indefinite integrals. What I mean by indefinite integrals are integrals without those terminals, or end and starting and end points. Okay, another cool rule is that we can reverse a terminal, right? So if I'm taking an integral from a to b, so the starting value is a and then we're ending up at b, that's the same as taking an integral from b to a, but with a negative out the front. How can I show this? It's all to do with the fundamental theorem of calculus again. So a to b of f of x, right, like I said earlier, is equal to capital F of b minus capital F of a, right? Now, if I do the same for b to a of f of x, like so, that's just equal to f of a minus f of b. Now, I'm sure a lot of you can already see this, but if I try to factorize this expression just by taking the negative out, I'll get negative f of b minus f of a, like so, with a negative out the front. And you can see that these two are just, you can see that these two things here are just negatives of each other, right? So this rule sort of stands. Hopefully that makes sense. It is super useful for solving these multiple choice questions that I'll show you in a little bit. Some basic rules with an integral. These are just to follow. These are rules that you have to follow. They are in your formula sheet as well, but I would recommend memorizing them. Just because you don't want to be in exam 1 flipping through that formula sheet and trying to fit these rules to these weird integrals that they will give you. So it's better to just know them and understand how they work. And the best way to understand how they work is to just do a bunch of practice questions. Okay. All right. And this is just them in sort of like a different form. So I definitely recommend putting this in your bound reference and also this one in your bound reference. But more than that, I would recommend just understanding it entirely, right? Okay. So I sort of mentioned this, we can take an integral or an antiderivative between two bounds, right? And that just happens to give the area under the curve. Now I won't go into the reason as to why that gives the area under the curve, but if you are interested, there are really good explanations online that sort of go into this. The only reason I won't go into it is that it's out of the scope of methods, and it's not really something you need to know, but if it is out of interest, a quick Google search generally gives you a good answer for that. Okay, so I've sort of already mentioned the fundamental theorem of calculus, just shown here, and I've written out plenty of times earlier. So hopefully that makes a little bit of sense. So again, capital F of x is just the antiderivative of lowercase f of x. Now, in this case, you guys would have noticed that plus c is gone. The dx still remains because we're just saying what we're actually integrating, and in this case, we're integrating a function with x, right? But we can get rid of the plus c. And the reason that is that plus c sort of cancels out. So if you guys go ahead and try to do this, you will see that the plus c cancels out. So we'll see that with the first f of b, right, we'll get f of b plus c, right? That's the first sort of set. And then the next one, we'll get f of a plus c like this. And you can see here that the plus c's just cancel out. So there's no point including them in the first place. So for that reason, we sort of just don't include plus c at all. All right, let's go through an example question. If when you guys are watching the recording, feel free to pause maybe and type your answer in chat as well after you get a solution for it, or feel free to follow along. So yeah, either or is fine. I would definitely recommend having a crack at it first before just looking at my answer or looking at the way I'm doing it. Okay, so the question is, it's to evaluate a definite integral. So from 0 to pi on 2 of sine 4x plus 4x cubed with respect to dx. So what we're going to be using is that table that I showed you guys a few slides earlier, and also the fundamental theorem of calculus to sort of evaluate this expression. So the first step is to integrate it, right? So to integrate this, I just used those the integral table that I showed a little bit before. So if we integrate sine 4 of x, we get negative 1 on 4 cosine 4x. And if we integrate this, we just follow the integrating a polynomial rule. And so we add 1 to here and then divide by that. right? So we add 1 to the top, so 3 plus 1 is 4, divide by 4, and we get this, right? Relatively simple, hopefully. And then after this, now we apply the fundamental theorem of calculus, right? So what I've done here is I've subbed in pi on 2 into the calculated expression from earlier. Then I've subtracted that from subbing in 0. So really all I've done is f of b minus f of a, just following fundamental theorem of calculus, right? And then from there, it's a matter of evaluating it. Now, evaluating it can be a little bit challenging, especially with these sorts of long questions, right? Personally, when I did these in high school, I made a lot of mistakes in these sorts of questions. So what I would do is I'd actually write it out like this, right? I'd take it step by step. I'd break it down into smaller, manageable bits, and then from there, I'd start doing the hard maths, right? Like this 4 pi on 2, before even calculating what it was, many of you can probably just look at it and know what the answer is. I just solve like what 4 pi on 2 is, right? So I'll just write it out like this, right? Which is like a reasonably trivial calculation to do, but you'd be surprised at the sort of mistakes you guys would make under exam pressure. At least I was. I made a lot of silly mistakes, and so a lot of what my exam preparation was and my SAC preparation was just trying to cut down on those silly mistakes. Anyways, I'll probably talk about that a lot as we go through the session. I'll talk a lot about the methods I use to eliminate my silly mistakes, and maybe how you guys can apply that to your working out. So one method I always used was writing out my working out in every single step, right? Just because it helps with it. When you go back and read through your working out, you can sort of see all the calculations you've done, and then from there, see if you've made any silly mistakes and sort of make sure that you've done it correctly. Okay, so from there, you're just sort of evaluating all of this. So this is an exact value you guys need to know, and that's going to be 1 here. And that's also equal to what cosine 0 is, and that's also 1. And so from there, you can sort of just work this out. So hopefully that makes a bit of sense. And this is what our final answer would be. This also gives the area under the curve for this function from 0 to pi on 2. And when we evaluate that, we get pi to the power 4 by 16. So hopefully you guys got a similar answer. Okay. So this is just a multiple choice question from a VCE exam. So you guys can see 2019 exam 2. If you guys are interested in the statistics, like what like percentage of students answered A, B, C, or D, you can check that, or E. You can check that out on the VCEE website. They do obviously they show the correct answer. They don't show the working out too much, which is kind of annoying. But what they do is they do show you like the distribution of students of like where they who selected each option, which I think is pretty interesting. But yeah, if you guys are interested in that, check that out. Anyways, so how can we do this? So let's see what the question is asking us, right? So we're asked to find the integral of f of x, and we don't know what f of x is. They haven't told us what f of x is, and a lot of people would see this, freak out, and just skip it, right? But we're going to try to break it down and see how we can go about tackling these sorts of questions. So we've got f of x with respect to dx is equal to 4 from 1 to 4, right? We're taking the integral bounded from 1 to 4, okay? And they've also told us that from 2 to 4, it's equal to negative 2. And what they want us is to evaluate this. Okay, so how do we do it? Well, I want to try use these two integrals that they've given me and try fit that into this integral and try work it out. Okay, so what does this first integral tell me? It tells me that capital F of 4 minus f of 1 is equal to 4, right? The second integral tells me f of 4 minus f of 2 is equal to negative 2, right? And then if I work out what this integral is here, right, I get capital of f of x plus x squared over 2 integrated from 1 to 2. So now I just sub that in, and I will get this expression here. Then it's a matter of simplifying that expression. So I see I get f of 2 minus f of 1 plus 3 on 2, right? That's still not enough information for me to eliminate any of the options, which kind of sucks, but I guess we just have to sort of deal with it and work through it. Ideally, as you're working through a multiple choice question, you're able to eliminate options as you go, but with these sorts of questions, it's a little bit hard to do that. Okay, so maybe some of you guys can see where this is going, but we're going to be using simultaneous equations to work out what f of 2 minus f of 1 is equal to. So I need to manipulate these two equations to make the expression f of 2 minus f of 1, so I can sub that in. So what I do is I subtract the red equation from the blue equation, and conveniently when I do that, I work out that f of 2 minus f of 1 is equal to 6. And so then I substitute this into here, and I get 15 on 2. So my final answer is option E, 15 on 2. So hopefully you guys got a similar answer as well. Any questions with how, like the method I used to work this out, just drop them in chat and I'm happy to answer them as we go. Okay, another useful property of these definite integrals, right, is that we can use it to find the area bounded between two curves. A lot of you will be used to just finding an area bounded between, like a single curve. So you've got some curve like this, and maybe you're just finding it between the x-axis and the function, right? But what we can also do is if we have two functions like that, we can actually just, oh, that's a wonky line. I'll get rid of that graph. So if I have two functions like this, I can use definite integrals to find the area contained between those two functions, right? Which is quite nifty. There can be some practical applications to this, but in methods you don't really cover that. Sometimes they give you application questions where that's useful. Maybe you're trying to find the area of a garden bed or something similar to that, and that garden bed is defined by multiple functions. That's just an example of the sort of application question you could get here. So the way, like the general equation that we always use for this is that contained area is, well, first you need to solve for the x-intercepts, right? So lower x value refers to the lowest x-intercept between those two functions. For example, if I have a function like this, right, and I want to find the area contained, well, I need to work out what this x-intercept is and what that x-intercept is as well, right? And then from there, I can sort of work out that area in the middle. Okay, so you want to work out what those lower and x values are, and then you want to determine in that region which function is the upper function and which one is the lower function. So in this case, I'm going to call this line g of x, I'm going to call this line f of x. So we can see that in this region, right, from, let's say a to b, in the region from a to b, g of x is above f of x, right? And so g of x, in this case, would be upper curve, and we'd be subtracting f of x from that. Now, let's say I wanted to take the integral of a function that's like this from maybe here to here, right? So call this b again and a again, right? So so in the first period from that first intersection, right, in just this area here, the top function, let's say, is g of x, the bottom function is f of x. Right. Now, when we go here into this period, right, so let's just call that middle point C, from C to B, that top and bottom switches, right? So now we have f of x at the top, and we have g of x at the bottom. And when we do this, what we need to do is we need to split this up into separate integrals. I need to take an integral from A to C, and then from C to B to, like separate integrals, because we're changing the upper and lower. Hopefully that makes a bit of sense. Okay. So here's an example question. Have a crack at it, and we'll sort of go through the answer. Also, feel free to work with me along as I go through it. Okay, so what it wants is the area bounded by the lines of y is equal to x squared, y is equal to 0, and x is equal to 3. Ooh, that's sort of represented on this diagram here, the one that I've sort of scribbled on. Sorry about that. But we want this area here, right? So they said y is equal to 0, y is equal to x squared, y is equal to 0, right? And x is equal to 3, right? Okay. How can I do that? Well, I want to determine what the lower and upper x values are, right? So, well, the upper x value, right? So this is just the representation of the area, sort of. The upper x value is clearly going to be at 3, right? Because that's where that intersection point is going to happen, because that's where that line is, right? So this is at 3. It doesn't really matter what y value it is at, because we're not actually using that for the integral. The starting value at y is equal to 0, right, is at x is equal to 0, right, which is quite convenient. Okay, now the upper function in this case is x squared, right? But what's the lower curve, right? We never defined a lower curve. Well, the lower curve in this case, right, is going to be the x-axis, right? And the x-axis is given by the equation x is equal to 0. So that's why I subtract with 0. Okay. And so from there, it's just a matter of evaluating this integral and, using the fundamental theorem of calculus, summing values in, and then, giving your answer. Now, this unit squared stuff is not entirely necessary. I usually write it. Sometimes I'll write it like this, right? And now it's just out of habit. That's not something you need to write, and it's perfectly fine to not write it, because oftentimes you'll see in Vika's answers that they don't have that unit squared stuff. Sorry, they don't have that unit squared stuff, so nothing to worry about too much. But yeah, so you can include, basically my point is you can include it or you don't need to include it, doesn't matter too much. Okay, integration by recognition. So integration by recognition is a really common question type, and it's not a particular topic per se, but it's a really common question type. I've definitely seen it in a bunch of exam ones in particular. Why exam ones? The whole idea with integration by recognition is that you're given an integral that you won't usually be able to solve. Usually they're in the form of like some two functions multiplied by each other, like this, right? And a lot of people will be like, well, can't I just split that up into two integrals? No, you can't. They're not being added, right? They're being multiplied together. Okay, so the way we do this is this technique known as integration by, it's by parts, or IBP. That's out of the scope of the method study design, but there is also another way to do it. So the way methods wants you to do these questions is, well, first they'll give you a function to integrate, right? Well, differentiate. They'll give you a function to diff, and then from there you need to work back and find a different integral. For example, we have this part here, and it's usually part A. So they'll be like, differentiate some function, right? And then they'll say, hence find the integral of this, right? So the first step is to just differentiate, right? Do it in the order they want, right? So we're first going to differentiate x log base e of x. I think it's just the formatting, but this should have just been, natural log or log base e. Okay, hopefully that's not confusing anyone. Okay, so we're going to take the derivative of x log e of x. I'm going to give everyone a couple seconds maybe to just type in chat quickly what rule they think is being used here. If you guys said product rule, you would be correct. So since these are two functions being multiplied by each other and we're taking the derivative of them, we want to use product rule, right? So a quick recap of product rule. So if I have dy dx, right, where y is equal to two functions, u times v, the first thing we do is we do u times dv dx plus v times du dx. Cool, so that's all I've done in this part. All right, so once I take the derivative, I get 1 plus log base e of x. Okay, cool. And then we want to integrate it, right? So if I integrate log base 1 plus log base e of x, I get x log e of x plus c, right? And so then I can do a little bit of rearranging to work out what the log base e of x is actually after doing this, if that makes sense. So ideally we want to get, we got 1, I'm going to write it as ln. That also just means natural log. So we have our derivative as dd of x ln of x, right, is equal to this. Okay, and I want to integrate ln of x with respect to dx. Okay, so what do? I rearrange this equation for ln of x. So ln of x is equal to ddx x ln of x minus 1. And then I substitute that into there. And so then this integral is equal to dd of x times x ln of x minus 1 dx. Okay, and so when I take the integral of a function that's being like derived, I guess, like that, the integral and the derivative just cancel out. So what I'm left with is x ln of x plus c, right, minus the integral of, oh, you can't really see that, but basically it's just this line here. So x, x ln of x plus c minus the integral of 1 dx. The integral of 1 dx is just x, okay? So that's just x ln of x minus x plus c. Sorry, my writing covers that, but the answer is still the same. Cool, hopefully that makes sense. And hopefully my scribblings aren't getting in the way. The scribblings won't be there on the notes, but the notes will have the full solutions. Okay. Another application of an integral is to find the average value of a function. You might have heard the term average value pop up with sine and cosine functions. So if I have a sine/cosine function that looks a bit like this, right? A lot of you already know that the period is equal to 2 pi on n. The amplitude is a, and the plus c is what we call the center, right? Or it's also known as the average value of the function, right? So average value of the function. So if they give you like a question that's like, maybe the temperature is modeled by a sine graph, and they'll be like, well, what's the average temperature? Well, that's just whatever the plus c or the y translation is, right? Well, another way we can work out what plus c is, or not plus c, sorry, another way we can work out the average value of a function, because maybe, it's like some, function like this, yx squared plus 2, it doesn't fit a sine graph, right? So how do you work out the average function? Well, we can use an integral for that. So the equation for an average function is this, right? So what it actually does is, well, this integral here finds the area, and then it spreads it out using this 1 over b minus a, right? So remember the area of a rectangle, or the area, I think area in general, right, is just height times width, right? And so what we're really doing is we're doing h is equal to a over width. Area we calculate from the integral, the width is given by b minus a, right? And that finds the average height of that function, right? Which is also the average value. Cool, hopefully that makes sense. All right, let's have a crack at this question. So they want us to find the average value of 1 over x over the interval of 2 to 5. Okay, so first thing I like to do is write out my expression. Sometimes in an exam, what I would do is just write out the actual equation as well, right? So I'll have a to b. So what I mean by the actual equation is just like the average value equation, right? So I'd write this out, and then I'd substitute my values in, right? So maybe even in the question when I'm reading it, I'd annotate what a and b are, just so that when I actually answer the question, I'm not missing, key pieces of information, and I'm not just randomly putting things in places where they shouldn't be. So I annotate the question, and then I substitute my values in, hopefully correctly, and then it's just a matter of integrating, right? From that table, that integral table that I showed a while ago, the 1 on x, you can't just integrate it like this. Ooh, don't know what happened there. You can't integrate it as if you were integrating x to the power negative 1. Just simply, and you can't integrate it like a polynomial, right? If you have 1 over x squared, you can convert that to x to the power negative 2 and then integrate that like a polynomial, because you add 1 and divide it by 2, divided by the resultant, which in this case would be negative 1. But with this, if you add 1, this is just x to the power 0, and you can't divide by 0, right? Which is why we have, well, it's not why we have, the integral being log x, but luckily the derivative of, the integral of 1 on x ends up being the natural log of x, right? So that's just the natural log of x. Let's quickly write this out like this, right? And so that's all that's being used to convert from here to here. And then we just substitute things in using the fundamental theorem of calculus. And then it's just a matter of solving. So the way that we simplified this to here was just using simple log laws. If you don't remember this, I would suggest revising it. So when we're adding two logs together of the same base and the same multiple at the front, we multiply. When we're subtracting two logs, we divide the inside product to simplify. Okay, and that's sort of it with integrals and integration. Obviously, I haven't gone into a lot of detail regarding integration, I haven't talked about the wide application type questions, but you'll see plenty of those when you guys go through practice exams and textbook questions. We didn't go through them just because this is meant to be sort of like an introduction to these topics, and not like like a deep dive into them. Um, but yeah, definitely check out your practice exams, and other there's like 8 on Notes resources that go through these in a lot of depth, in terms of like question styles. So we've sort of given you guys all the information you need to tackle these sorts of question types, but it's always a good idea to practice these question types, right? So that when you see them in an exam, you're not sort of like panicking and you're not really sure where to go. It's just a good idea to expose yourself to a variety of questions so you can sort of draw similar connections to questions that you see in your actual exam. Okay, now to start with probability. One thing I'll sort of preface this with is that a lot of people kind of think probability is going to be their worst topic, just simply because I feel like from like maybe year 10 onwards, probability does get pretty hard, right? Personally, I sucked with probability, so even in year 11, I really sucked with probability. So when when year 12 came around, I sort of thought, maybe I've really got to like crack in, because I've got to do well, right? And so what I did was, because I really sucked at probability, that's a bit of an understatement, I decided I'd do every textbook question on probability. And so if you find yourself in a similar boat, maybe you're hating probability and you're thinking you're really bad at it, it's often just a good idea to just do every single textbook question on it. And I know that sounds insane and a lot of work, but in the end, it did pay off. I think probability ended up being like my best section in terms of both SACs and exam, just because probability is one of those sections that's really repetitive. What tricks people, and even me still now, is the wording, right? And there's only so many question types they can ask you with probability, and the textbook generally contains them really well. So just doing a bunch of questions from the textbook, a bunch of past exams, will set you up really well for probability. Whereas with integration and other topics, they can ask you like really weird novel questions. They really can't do that with probability, and they're often just repeats of each other with different values. With that rant over, we'll sort of get into it. Okay. So what is probability? Probability is the likelihood that an event will occur, and it's always like placed on a scale from impossible to like certain. So 0% chance to 100% chance, right? So the probability of an event X, right, is the number of the times event X happens divided by the total number of events. For example, if I flip a coin 10 times and I want to know the probability of getting tails 5 times, I need to flip it 10 times and measure the probability, right? Or measure, like, take account of how many times tails has popped up, and then I divide that, theoretically it would be 5, right? And so I'd do 5 divided by 10, and that'll give me the probability of getting a tails. And generally we measure probability in decimals or fractions. Sometimes you'll see them in percentages though, and so it's really important that when you see a percentage, to convert it back into decimal, right? So sometimes you'll see like a statement like 50% chance of X happening, right? But it's a better idea to convert it to decimal because those calculations are easier to deal with. Even though I've said that, decimals are kind of bad to deal with. So what I would do is in exam 1, I'd generally deal with fractions. But in exam 2, often you're given horrible numbers that only simplify to decimals in your calculator. But yeah, generally try keep them in fractions, especially even in exam 2, because they will ask you, like when you guys do exams, you'll probably see this little like text section at the start, which says, give your answers in exact form unless specified, right? Sometimes in the probability section, they'll ask your answers to 4 decimal places. But most times when nothing is specified, you need to be giving your answer in exact value or in fractions, right? So keep that in mind when doing these questions. But fractions are just easier to deal with, especially when you don't have a calculator on hand. There are some exceptions though. Another thing with probability is that it needs to, the probability of an event happening can only be between from 0 to 1, right? Which makes sense. 0 being impossible, you can't be, less certain, like you can't be less likely than impossible, right? And 1 is certain. You can't be more possible than certain, right? If something is going to happen, there's no way, like, there's no like way to increase that chance from 100%, right? Another thing is that this is just sort of complicated sort of symbols that you guys will see in the questions. But basically, this sign here is sigma, right? For those of you who haven't seen it, basically just means the sum of, right? So if I have, like the sigma of some set, that just means you're just adding every value in that set, right? So maybe, the sum of some, like the sum of ni, where n is like a set of where I is equal to 1. Maybe like, when n is like a set of 1, 2, and 3, right? This is, the notation's not entirely correct, but hopefully this will help you get a gist of it. You're just doing 1 plus 2 plus 3, right? It's not entirely correct, but that's just the gist of it, right? You're just summing all the probabilities up, or summing all the values in that setup. And so what this whole statement is saying is that the sum of all the probabilities must add up to 1, right? So if I have, like 2 events, so if I have an event, like the probability of getting heads and the probability of getting tails, well, they both need to add up to 1, right? Like, it can't be like this, right? Because this only adds up to 0.7, and that doesn't explain what happens, the 30% time, right? If I flip a coin, I'm only going to get heads or tails, right? It's so unlikely that it just lands on, like, the ridged part of the coin, right? So for simplicity, it's always going to be heads or tails, right? So it doesn't make sense that heads or tails only occurs 70% of the time, right? Which is why this needs to also be 0.5. All right, hopefully that makes sense. So all the events, the probability of all events needs to sum to 1. This is just that sort of displayed on a scale, right? 0 is impossible, 1 is certain. These are just general terms that you don't really need to know, but I think it's a good way to sort of describe what's happening in an intuitive sense. Okay, let's just revise some key terms for probability, and I'm sure you guys would have seen these terms before, but I think it's a good idea to recap them before diving into 3-4 probability. So a random experiment is an experiment with a random outcome. So let's say you have a jar, or like a bag of socks, right? You have like 20 different types of socks with 20 different colors. You just put your hand in, you're not looking, you're just digging around, pulling out a sock. That's entirely random, right? Outcome is the result of a random experiment, the color of the sock, or in this case, the color of the jelly bean. Sample space is every possible outcome of a random experiment. So maybe in my bag of jelly beans, or in my bag of socks, I have socks that are colored red, blue, and green. So the sample space would be pulling out a red sock, pulling out a green sock, or pulling out a whatever other color I said. And an event is a single outcome. So, for example, if I pull out a like a green sock, that is an event, right? Also, let's say I'm interested in the probability of pulling out 10 green socks, or like 5 green socks in a row. Pulling out those 5 green socks in a row is also an event. Okay. Another thing that's super important with probability is set notation. I'm sure you guys would have come up with union and intersection before, and it's really useful to explain them in terms of Venn diagram, but it's also, you probably would have seen them with function notation as well. So A intersection B is a list of outcomes that are both in A and B. So what that means is if I have a Venn diagram of A and B, the intersection is that red area that I've shaded. Union is A or B, right? So it's whatever is in A, and it's whatever is in B. So it's just whatever's contained in the Venn diagram, right? So intersection, it's good to think about it as like an and thing, where so you can see here or and, so it's and, whereas union is an or sort of statement, right? it's one or the other in union, or it has to be, both of them together in intersection. With union, we have this really nifty rule, sort of, that you can use to sort of calculate what this is. There's a cool proof you can sort of do with the Venn diagrams, and I'll sort of go through that now. So if I have, two Venn diagrams like so, if I want to work out what the total area is covered between them, but I only know the probability of A, the probability of B, and the intersection between them, if I want to work out the union, well, it's sort of useful to like split it up into two sort of Venn diagrams, or two circles, sorry. So I'm going to split this up into two circles. Let's just ignore the intersection at the moment, right? So I know what the probability of A is, and I know what the probability of B is, right? And so I'm going to add those together, and that's what this is, right? I'm getting those two circles, and I'm adding them together, right? Now, when I do that, you'll notice that this section here and this section here, the sections that are going to form that intersection region, there's two of them, right? There's some of it contained in B, and there's some of it contained in A. And so when I overlap them, I get sort of a doubling up, right? And you can see my fingers are doubled over, right? So I get a doubling up. And to get rid of that double up, because that's not counted in a union, right? Like when you do a union of a set, you don't count double ups, right? So to get rid of that double up, we subtract one of the intersections. So I have a double up, and I subtract it, and now I'm just left with, A union B. Hopefully that makes sense. And then a complement is just the opposite, right? So everything, a complement is everything that's not an A. And we can also represent that by this sort of equation, which makes sense as well. So if, the probability of A happening is like 0.8, well, the probability of anything but A happening, because it all needs to add up to 1 at the end of the day. So the probability of A happening and the probability that A is not happening must sum to 1, right? Because one of those events will happen, right? And so you just need to sort of reshuffle it, and then what you'll get is 1 minus 0.8, which is just 0.2. Okay, and a little bit more terms. I know basic probability is just a lot of memorization, but trust, once you guys get to the cool stuff with discrete, binomial, and continuous, I think it's quite worth knowing these. Okay, I've potentially had a lot of questions about mutually exclusive and independent. Like, what's the difference? So mutually exclusive is if they can't occur together, right? For example, if that intersection is 0, right? So A intersection B is 0, right? So if I've got something like this. Independent events, on the other hand, are when one happening doesn't affect the chance of another happening. A really good example of that is something like me solving a Rubik's Cube in like a minute, and the probability that it rains, right? It's likely that when I'm solving the Rubik's Cube, I'm inside my room and not affected by the rain. And me solving a Rubik's Cube faster or slower is not going to affect the chance that the rain happens, right? So in that sense, they are independent, right? Their probabilities aren't linked. Now, if they're mutually exclusive, it's one or the other. There's never an overlap. For an example, maybe it's like playing cricket and it raining, right? It's like when that intersection is 0, right? Then they're not, well, it's really unlikely that they're going to play cricket when it's raining. And, let's just, for the sake of simplicity, let's say it's 0, right? So if it's raining, they're not playing cricket. If they are playing cricket, it's not raining. So it's a bit of like a logic sort of puzzle, I guess. But mutually exclusive just means that there is no overlap. They're just two distinct events that can't, it's like a yes or a no, right? Or it's an incorrect and a correct. I guess you can be like sort of correct, but if we're just looking at correct and incorrect as like two discrete sort of things, you can't be incorrect and correct. There's no overlap, right? Hopefully that makes sense. But independent, it's just that, the chance of one happening doesn't affect the chance of another happening. Now, cool thing with this is that if you have two mutually exclusive events, their union, right? The union of A and B is just probability of A plus the probability of B, right? We don't have to subtract the A union B because that's just equal to 0, right? So it's sort of pointless to represent that. Now, a condition with independent events, right, as you guys can see here, is that their intersection is a multiplication of each other, right? So it's just the probability of A times the probability of B if A and B are independent. So a super common question type I've seen is that they'll give you two events. They'll say that the probability of this happening is like 0.8 and the probability of this happening is 0.2. Are these events independent or not? And maybe they'll also tell you the probability of like an intersection. So for example, the probability of A is 0.8, probability of B is 0.2, and their intersection, A intersection B, is equal to 0.16, right? The way you'd prove that, these two are independent events is you'd throw it into this equation. And then you'd have to show that A union B is equal to these two multiplied. A intersection B is equal to 0.8 times 0.2, which it is. So in this case, A and B are independent. But sometimes you can have a case where, it's like A is 0.8 again, B is also 0.2, but their intersection might be like 0.05. And obviously, in this case, when you multiply 0.8 by 0.2, you don't get 0.05. So in the second case here, they are dependent events. Okay, cool. So we can also show that with a Venn diagram, which I've already sort of done. We can say that this area is A, this area is B, right? And when I do this, and when I want to show how this rule works, you can see that I've scribbled in this area twice, right? So I want to subtract that area again. Sort of already been through that. It's always a good idea when you get a sample space of multiple events, if you can represent it with a Venn diagram, just because it'll make doing those calculations a bit easier. It's always a good idea to take a load off your brain, more or less, right? You don't want to juggle so many things in your brain. That's just a recipe for silly mistakes. Okay, let's talk about conditional probability. Conditional probability, super common, pops up everywhere. Really nice question type, but enough about me talking about the question type and how it's nice. Let's talk about how we can do these. So what does conditional probability mean? It's the probability given a condition, right? Which sounds like a cyclic definition, but let's say, the probability that it rains given that it rained yesterday, right? So I'm giving you an extra piece of information to sort of deal with, right? And that generally works in a sense that when the event that occurred previously changes the event of, the probability of a new event occurring, right? So for example, in this example here, you're going to roll a die and I tell you it's an even number. So what's the probability that it's a 4? Well, let's say it's a 6-sided die. The sample space of this die is 1, 2, or dice, sorry, 4, 5, and 6, right? So that's the sample space of all the possible numbers. Now I tell you that it's an even number, right? So all the even numbers are 2, 4, and 6. Now if I want to work out the probability that it's a 4, so the probability that it's a 4, given that all of these are even, right, is, well, I look at how many times 4 happens in the original set. Well, that's just, and how many times it happens in the second set. I look at their intersection. In both, it only occurs once. In the top, I have 1, right, which makes sense. Probability of getting a 4 on a 6-sided dice is 1, right, just rolling it randomly. But it's not 1 and 6 because I've changed that sample space. I've decreased it, right? I've taken it from, just 1 to 6. I've said, well, it has to be an even number. So it's either 2, 4, or 6. And so there's 3 possible outcomes, right? So I write that down. So the probability of getting 4, given that it's an even number, is 1 over 3. And so that's nicely summarized in this rule here. So A given B, right? So it's written as A given B, is equal to the, that's meant to be up there, but I'll rewrite it so it makes more sense. So the probability of A given B is equal to the probability that A intersection, or the probability of A intersecting with B, divided by the new narrowed down sample space, which is given by the probability of B. Also, some of you guys would have noticed that I'm writing it, I'm not writing PR, I'm just writing P. Doesn't matter, either or, they're the same. At university, for some reason, we were just taught to write it with a P. It doesn't really matter, I guess. I'd recommend just doing whatever your teacher does. This is the way I've done it, but either or I think is fine. And considering we did it at uni, I hope it's okay. Okay. All right, cool. All right. Another way we can display things, apart from a Venn diagram, is known as a Carnot map. So Carnot maps aren't explicitly on the study design. I want to make that clear, but I think they're a really good way of sort of representing these questions, and they definitely sort of really helped me during my exam. There was like the need to do a Carnot map, and a lot of my friends didn't love that question. I didn't like that question either, but a Carnot map sort of helped me get through it. Okay, so what is a Carnot map, or probability table, right? It's, well, we represent all our possible events, and it's really convenient for 2 events, but you can do it for multiple events, right? So you can maybe have A, B, C, right? You just need to add an extra sort of layer to it. So these boxes are just the events, right? And the boxes that sort of like intersect with them are their like literal intersections, right? So this box here is A intersection B. Here is A intersecting with not B. Here is not A intersecting with not B, and so on. So when these two add, right, we get the probability of B, right? The probability of A intersecting with B and the probability that not A intersects with B. Both of that is going to give the total sum of B, right? And same here, right? Those sum up to equal this. And then these two sum up to equal the probability of A, and these two sum up to equal the probability of A. And nicely, we expect that it all sums up to 1, right? Because B and not B must sum up to 1, and A and not A must also sum to 1. Okay, hopefully that makes some sense. So let's have a go at using it on a question. So the probability that Joe rides his bike to work and it is sunny is 0.1. So we've got 2 events that we can sort of characterize here. One event is that it's sunny. The other event is that Joe rides his bike to work, right? So I'm going to call that S and B. With probability questions, it's always helped me to sort of highlight everything, annotate everything, just break it down from, instead of this big slab of text, right, that's really annoying to read, just breaking it down to key pieces of information that you need and not all the random stuff. Like, you don't need to know what the guy's name is, right? What you need to know is the 2 events, right? And the numbers. So the probability that Joe rides his bike to work and it is sunny, right? And, okay. So that's the intersection event between the B intersection S is equal to 0.1. So I'm going to write that in my table, 0.1 here. The probability that it isn't sunny, so not sunny, and the probability that Joe rides his bike, so S intersection, intersection B is 0.7. So 0.7 here. Using a Carnot map, what is the probability that on any given day he doesn't ride his bike and it isn't sunny? Okay, so how can I do this? Well, here is 1. And so this is just 0.1 plus 0.7 is equal to 0.8, right? 1 minus 0.8 is equal to 0.2. Now let's see if the question has given us any additional information. The probability that Joe rides his bike to work and it is sunny is 0.1. Okay. The probability that it isn't sunny. Okay. I think I've misread the question. Which happens. I've realized there was, from what I looked at, there was insufficient information to answer the question, which is kind of unlucky, but that's fine. So I think it said the probability that it isn't sunny is 0.6. So what this is not what I've written out here. Oh, sorry, just zoomed in. I think this is just S. The probability of not S is equal to 0.6, and the probability of B is equal to 0.7. That's my bad. I'll quickly rub this out. But yeah, there you go. You guys can see just how easy it is to misread these probability questions, lose a couple marks. So it's always a really good idea after you tried answering the question, you sort of stuck, go back to the question straight away and try work out what mistake you've made. Okay, I still think this is correct, right? The intersection between B and S. So the probability of B is 0.7. The probability of not S is 0.6, right? So I think this is a little bit more plausible and easier to work out. So just 1 minus 0.6 here would give me 0.4 for the other event, and here is just 0.3, right? Because 0.7 plus 0.3 sums to 1. Here, I just need to do 0.7 minus 0.1, so 0.7 minus 0.1, and that's equal to 0.6, which I think is going to give me 0 here, right, if I haven't done that incorrectly. And so here, I should be left with 0.3. If I made any mistakes, by the way, with any of these sorts of questions, just throw a message in chat. Yeah. Okay, and this is just going to go through that, sort of worked out. But hopefully that makes a bit of sense. Okay. And so then we can use this table to help us answer questions, right? This table isn't just for the sake of making it, it's also for the sake of helping us answer questions. So they've said it is sunny today. What is the probability that Joe rides his bike? So sunny intersecting with riding bike should be 0.1, right? But what it's also important to know is that they've sort of told us a condition. They've given us the condition that it is sunny today, right? So this implies conditional, right? Because they've given us an extra piece of information. So what we need to do is we need to use our conditional probability equation. So riding bike, given that it's S, right? Given that it's sunny. So on the top, we want to know the intersection between B and S, and I said that was 0.1, so we write 0.1. The probability that it's sunny is 0.4, and so simplifying it, we'll just give 1 on 4, or a quarter, or 0.25. But yeah, I've always found these tables to be helpful for these conditional probability questions, mainly. Okay, let's talk a bit about independent events again. So like I mentioned, if 2 independent events are occurring, the probability of one happening doesn't affect the probability of another happening. So if I've got the probability of, like a conditional probability, so I'm saying probability of B given A, that's, the probability of B occurring is not going to affect the chance of, the probability of A. So that doesn't affect anything. This also applies, right? So the probability of A intersection B is equal to the probability of A, the probability of A intersection B divided by probability of B is equal to probability of A, right? Which makes sense from our equation earlier, right? If you remember, I think maybe 2 slides ago, I might have quoted the same equation there. See, that's derived from the previous one. Just simply because they're not conditionally linked, right? If I tell you that, in like the last scenario, right, clearly there was some link between the weather, like it being sunny or not, and the person riding the bike. But if we go back to my example of me solving a Rubik's Cube in X amount of time, maybe like a minute, I think is what I said, and it raining outside, those are clearly not linked events. So given that it is raining, the probability of me solving my Rubik's Cube in less than a minute doesn't change, right? Okay, mutually exclusive. This is what it looks like on a Venn diagram. I sort of already mentioned that. Their union is just adding the probability, A and B together. Oh, okay, cool. All right, another technique to know is tree diagrams. So what's a tree diagram? It's a map of all possible events, right? They're generally useful for 2 to 3 events, and not anything more than that. So event A is that first branch, and then event B is the second branch, right? And it's all given in conditional probabilities, right? Because what this is saying is that B happens given that A already happened, right? And so from there, we can multiply the probability of these 2 things, right, to give us their intersections. Okay, hopefully that makes some sense. Another useful note to know is that if you have something with the words and, so if I want something to happen and another thing to happen, so for example, the probability of me solving a Rubik's Cube in less than a minute and the probability of it raining, then I multiply them together. When we use or, so the probability of me solving a Rubik's Cube in less than 1 minute or it raining, well, for that you use plus. And hopefully these and or sort of things ring a bell. And is an intersection, right? And is intersection. And or is union. So general rule of thumb, if you see intersection, you're multiplying. If you see union, you're adding. But remember, the intersection multiplying thing only works for independent events. Okay, random variables, what are they? A random variable, more or less, is a variable that's defined through like a function, right? But this function is defined on the outcome of an experiment, right? So it's a little bit more complicated than your standard variable, but it's just complicated terminology for something that's reasonably understandable. So an example here is that if you flip a coin 3 times, your outcome, right, is going to be the set of 3 coin tosses. That's either going to be a heads or a tails, right? And so you could make a random variable, right? And that random variable would be something like I said earlier, as the number of heads that are going to pop up, right? Or maybe the random variable from my example was the probability that I solve a Rubik's Cube in less than a minute. Maybe I tried doing it, like scramble it 5 times, try solving it 5 times. And so the random variable could be, solving it in less than a minute. And here are just a couple examples of some random variables, right? So hopefully that sort of makes sense. I would recommend throwing these definitions on your bound reference, just in case you have a mind blank in the exam, but I would really want you guys to memorize this sort of stuff. Okay, with random variables, they are generally represented with x, but I've used different variables all the time, especially for spec. Sometimes you get a few different variables, so you can just use different letters. Doesn't actually matter. It's just an arbitrary thing that we choose. Same with like f of x, right? You can really use any variable you want, but it's just x seems to be the favorite variable for mathematicians in methods, anyways. So what that means, like how is it represented? Capital X is the random variable, whereas 2 is like the particular event, right? So the probability of x is equal to 2 just means that the probability that our outcome is equal to 2, right? X is equal to green is the probability that outcome is equal to some defined thing known as green. Okay, mean, median, and mode. These are definitely things you guys have seen before, but I'm going to give it a little bit of a different twist on them, especially in discrete and the other stuff that's come. So mean, please remember this symbol. It's how we represent it in methods. That's called mu. The way I usually write it is just like a U, but I start with like a tail out the front, right? So the mean measures the center of the distribution, right? And it's also known as the expected value. Hopefully this rings a bell to an integration sort of technique that we talked about earlier, or the average value of a function. When we talk about continuous probability, this can be pretty important, so keep that in mind. It's also denoted by E of x, and E of x just means the expected value of x, right? It's because the average and the expectation are about the same. The median is the value that there is 50% of the values lie above it and 50% lies below it. So if I have 1, 2, 3, 4, and 5, the probability of 1 occurring might be 0.2, the probability of 2 occurring might be 0.2, and the probability of 3 occurring is 0.1. So then the median value is 0.3 because 50% of the probability lies sort of below it, 50% lies above it, less, right? So that's a median. Right, so in this case you got 1, 2, 2, and 5. 2 is the most likely common thing, so it's also smack bang in the middle, so that's the median. Mode is the most frequently occurring x value, or event value. So in the case of the last thing, the last one is also the mode, right? It's going to be 2 because it occurs the most, right? The value of x which has the highest probability, right? So maybe this is like 0.05, and maybe there's a bunch of more events of just 0.05 until it all adds up to 1. So then, the mode would either be 1 or 2 because it has the highest probability of occurring, if that makes sense. The mean, this is a little bit of a application style question that they can ask you primarily in your SACs. Sometimes they can ask you which of the mean median mode is the best definition of the center, right? And I think a lot of people would just go ahead and straight away say the mean, right? That because it's the average, right? But the problem with mean is that it's not robust. And what I mean by robust is that it can be affected, or not robust, sorry. What I mean by not robust is that it can be affected really easily by outliers, right? If I have, a couple numbers 1, 2, and 3, and also 0.00001, the mean is going to be so much lower than what 1, 2, and 3 actually are, right? Or if I have 1, 2, 2, and 5, and I don't know, like 0.0001, again, the mean is just going to be dragged down, right? But the median and the mode are just better sort of definitions of a center, right? The mode is going to obviously choose 2, which is probably closer to the center of the distribution, and same with the median. Hopefully that makes sense. Sort of a side note, but regardless, very important to understand, I think. Okay, how can we measure the spread of our values, right? Obviously, after we do an experiment, we're going to get a bunch of different values, right? How do we measure the distance between each value, like how each value varies with each other? And so that's where variance and standard deviation come in. So they're both measures of spread, right? So variance is given by the square of standard deviation, right? So we generally use variance to define a distribution. And we'll talk about defining distributions when we talk about binomial and normal, right? And standard deviation is usually denoted with an SD or lowercase sigma. Probably remember me calling this sigma. That's uppercase, and this is just a lowercase sigma. So variance can also be denoted as sigma squared, right? Because var of x is equal to sigma squared, right? From that. Variance is also represented with variance of whatever variable. So if your event is shown by y, you'd be dealing with var of y and not var of x. Okay. And standard deviation is SD or sigma. So standard deviation is always the square root of variance. So that says that variance must always be greater than or equal to 0, right? Because we can't take the square root of a negative number in methods. Okay, let's get on to discrete probability, right? So we've sort of covered, all the basic stuff. Now it's time to get into the nitty gritty. All right, what are discrete random variables? Well, discrete random variables has a few key properties. So it can only take countable values or whole numbers or, natural numbers, right? Or integers. Actually, I don't know if the last part came up in the recording. So natural numbers or integers. The probability of all of them need to sum to 1, right? Just before the basic probability sort of thing, all probabilities need to add up to 1 in, the total event or sample space. So I'll give you guys a couple seconds to have a read of this and maybe, choose which of these could be a discrete variable. So hopefully you guys have typed your answer into chat, and I'm going to sort of talk through each one, right? So the number of siblings, obviously, that is a whole number, right? You can't have 1.5 siblings, right? Same with houses. You can't have 1.5 houses. But with height, that's not so clear, right? So you can obviously have 1.5 centimeters or 1.5222 recurring, right? And if you went and arranged people in your class based on height, right, you'll see that you'll get like sort of like a spectrum of heights, right? You're not going to get defined groups. Maybe with eye color, you'll definitely get defined groups. You'll have a group of people who are definitely brown-eyed, and definitely a group of people who are green-eyed, right? But with height, if you choose a particular value in height, maybe like 181.2 centimeters, you'll be lucky to find one person with that height. That probability in a large population would be really close to 0, right? So with height, you'll probably be defining it by, greater than 180 centimeters or less than 180 centimeters. And that's where you can create groups. but you're not choosing exact value, you're choosing a range. So hopefully that makes sense. With discrete random variables, we can choose large or exact groups. Okay, so this is what a discrete probability table would look like, right? So we have our variable name here, and we have the probability sort of being like shown there as well. So x can take up the values of 0, 1, 2, 3, 4, 5, and each with its corresponding probabilities here, right? So all of these must sum to 1, which we can see, and all of them must be between 0 and 1. They can't be negative, they can't be greater than 1. Okay. Now, if we look at what's known as a probability mass function, which is just fancy speak for showing the probability on a graph, we can see that it comes in discrete lines. There's no in between, right? I can't be between 0 and 1. I can't be between 1 and 2. There's no smooth curve, right? It still shows, like a center, it still shows a median, right? But there's no smooth curve. You can only be 1, 2, 3, 4, or 5, right? You need to know how to draw out these tables, by the way. Always have x and the outcomes on the top and the probabilities on the bottom. Okay, how can we use this to determine probability, right? Because that's what we want to know. That's how we want to answer these questions. So we can determine it straight from the table, right? So if I read off the table and I look for probability of x is equal to 3, you just look at that. That tells me it's 0.3. There we go. That's my answer. But we can also, work out a range of probability values. For example, if I want to calculate the probability that x is greater than 2, maybe, don't have a look at that. Have a pause, have a think, maybe. If we look at it, what we're doing is it's x not inclusive of 2, right? So I can't include 2, so I scribble that out in my mind. So what I'm doing is I'm doing 0.3 plus 0.4, right? So 0.3 plus 0.4, and that's just equal to 0.7. So how can we work out mean, median, and mode for this probability table? I sort of did a small example earlier, right? But it wasn't in too much detail. So let's start with the median and mode, right? The easiest ones to work out. The median is the middle number. We want 50% of values greater than the median, right? So, shouldn't reveal that. I want you guys to have a sort of think about, which ones here could be the median, which ones could be the mode. So you want to add these up and work out where that 50% mark lies for the median, right? So we're going to go, the way I like to start is I start on the left and I just keep adding until I get to 0.5. So I have 0.1 plus 0.2, which is 0.3, plus 0.16. So that's 0.3 plus 0.16, which is 0.46, sorry. And then I can add the 0.24, and that's going to be greater than 0.5, right? So clearly that median is in between 3 and 4, but since I'm dealing with discrete variables, I can't have a thing between 3 and 4. So I'm going to say 4 is my median, right? Because 50% lies below and about 50% lies above, right? And to work out the mode, I want the most popular number, or the number with the highest percentage chance of happening. If I look at these, 0.24 has the highest chance of occurring, and so then that must be the mode, right? And so, your answers for both A and B are 4. But how do we work out the mean? So with the mean, there's actually a formula to do, right? And that changes based on what sort of distribution it is, whether it be binomial, continuous, or normal, or discrete. We have a different equation to use. So when we're using a table, we want to use this freaky looking formula, right? What this says is you want to take every single x value, multiply by its probability, then add it together, right? So the way you'd read it, like I just said, sum of x multiplied by its corresponding probability. So let's try to work out the mean for this, right? So how we would do that is I'd multiply these two values together, then add that to these two values together, and then add it to these two, and add it to these two. Why do we multiply by the probability? Well, in general, right, when we want to work out the average, we want to take up all the, all the values, add them together, divided by the total number of, the chance of that value. So sorry, let me rephrase that. If we want to work out the average value of a set, right, or a sample space, we sum up all those numbers and then we divide it by the total number of those things happening, right? The number of numbers in that set. But with this distribution table, we don't know anything about the set. We only have the probabilities. So by multiplying the probability by, the event number or the outcome, what we're doing is we're weighting that outcome, right? We're weighting it with its probability, which is why we do it like so, if that makes sense. So the number with the highest probability is going to be weighted more heavily. So it's more likely that that will be the dominating value when it comes to the mean. By dominating, I mean that means that the average is going to be closer to that value. And so you can see here, all I've done is 1 times 0.1 plus 2 times 0.2 plus 3 times 0.3 plus 4 times 0.4. And using that, the mean has worked out to be 3, right? Which is pretty neat. Okay, how can we work out variance and standard deviation? Sorry, that's sort of cut off. Hopefully it's still readable. So with variance, right, again, it's like the mean, it changes based on the sort of, distribution it's in. But for discrete, it's also really ugly, right? It's e of x squared minus e of x squared, right? So we're first doing, what this is the expectation or the expected value of x squared minus the expected value of x whole thing squared. So if you guys remember, e of x is just equal to the mean, right? So how do I work out e of x squared? And it's not just the mean squared, okay? E of x squared is that we need to make a new probability distribution table with every value squared, and then we just work it out as per normal. So we sum up the squares of the variables and their respective probabilities, then we square the mean. So how would this work out to be? I'll give you guys a couple seconds, maybe have a crack. But let's try to work out the variance, sorry. So how does e of x squared work? Well, all we do is we just square these values here, right? And then we still multiply them. What I like to do is make a separate table for this, right? So on top or on bottom, I'd make an x squared set. And so then I'd just write 1 squared, 2 squared, 3 squared, and 4 squared. Obviously, I can do 4 squared in my head, and that's not the issue. What is the issue is that maybe I might make a silly mistake, right? So again, I don't want to do any thinking, more or less. I want to put it all on paper, so I'm not juggling variables in my head, and by not juggling variables in my head, I'm not screwing things up, right? So I'm just going to, write things like so. And then I need to work out e of x squared, I just do the normal calculation. I'm just multiplying them together, like so, and we get 10, right? And then to calculate what e of x whole thing squared is, that e of x squared like this is just the mean squared. So what we worked out last time, right? So that's just 3, we're squaring it. So we apply it to the equation and we get 10 minus 3 squared, which is 10 minus 9, and we get 1. And if I want to work out my standard deviation from this, right, my standard deviation is just the square root of variance, and so my standard deviation is just 1 here as well. Okay, let's have a go at this question. I'll give you guys a couple seconds, have a crack, maybe pause it, type your solution in chat. Only reason I say type your solution in chat is so that you guys sort of lock in your answer and get a very accurate reading of how you guys went. Maybe also see how other people's, what other people also thought was the answer. Just because, it can like, even if other people or you get the answer wrong, there's nothing wrong with that, right? What I want to reinforce is that getting a question wrong isn't, like, oh my God, I suck. It's more a learning experience, right? It's getting a question wrong is probably the best way to improve. Because when you see what went wrong for yourself or what went wrong for others, you can sort of see where they've come from or where you've come from as well in terms of thought process, and you can sort of refine it, right? So you can sort of refine that process, and you can also notice where your mistakes are coming from and eliminate those mistakes. Okay, enough about me rambling about that. So a discrete random variable x has the probability function, probability of x is equal to k. And that function is given by, this gross equation, that gross equation there, where 1 minus p to the power k times p, where k is a non-negative integer. The probability of x is greater than 1 is equal to, okay, so we've got to try and work this out. So we've got a discrete random variable. That's the first thing I want to highlight, right? You can only, I don't have to deal with 1, 1.5, 1.75, right? I'm just dealing with 1, 2, 3, and 4, right? Also, it's important to note that since I'm dealing with x is greater than 1, right, that's also equal to x is greater than or equal to 2, right, because there's no 1.5 sort of terms that I was talking about, right? So what I want to do is, and also the other thing to note is that I don't know the upper bound, right? This could have 10 possible, values. So maybe it goes 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Maybe it goes to 12. Maybe it goes to 13. I don't know where that upper bound is, right? So I can't just keep adding things. What I do know is that 1 minus probability of x, so 1 minus probability of x is less than 1, is sort of like the flip, right? This is just equal to the probability of x is less than 1, right? So I can sort of use that to work this out, which is what I've done here, right? So I've written it out like so. So the probability of x is greater than, oh, sorry, that is not what I meant to write. I was meant to write that the probability of x is greater than 1, right, as said above, is equal to the probability of x is greater than or equal to 2. If x is greater than or equal to 2, it's every value in that set except x is equal to 0 and x is equal to 1, which is why I subtract that here from 1, right? Everything but that, right? So 1 minus that. So I substitute in k is equal to 0 and k is equal to 1. And so after doing that, I can quickly drop this out. So after doing that, I can sort of sub everything in and work it out from there. So my answer here would be E. This is definitely a tricky question. So another thing I'd recommend adding into your bound reference is these tricky questions. It's reasonably useful to add in tricky questions into your bound reference. So if you get a similar question on your actual exam, you can sort of just flick back and refer to the method you used to solve that question as well. Okay, so that's all there is really with discrete probability. It's just a lot of practice. It's good to expose yourself to a variety of question types. Like this is a really tough question. And I don't think I've seen anything like this outside of VCA. So yeah, very good question to do that. Okay, so let's now talk about binomial distributions and Bernoulli sequences. So what is a Bernoulli sequence, or what even is a binomial distribution? So bi meaning two. So a Bernoulli sequence follows this thing known as a binomial distribution, but I'll talk about that in a bit. Let's sort of focus on Bernoulli sequences. So a Bernoulli sequence has a certain rule, right? So any Bernoulli sequence has two outcomes, right? And we can define these outcomes as a success or a failure. For example, let's say I flip a coin, right? And let's say I said getting tails is success and getting heads on the coin is failure, right? So two distinct outcomes, I can easily define them as successes or failures, right? And every time I flip that coin, the probability is the same. Every trial needs to have a constant probability. And each failure is also a constant probability. So coin is really good for this because regardless of the number of times I flip that coin, that probability isn't going to change, hopefully. And these trials must also be independent. So the probability of the first trial must not affect the probability of the second trial. This is quite a a lot of conditions to meet, but they're nice conditions to have because they let us put in place a pattern more or less. Like I said, a sequence of coin tosses where each head is a success, or and each toss is independent, right? So multiple Bernoulli sequences allow us to build what's known as a binomial distribution. So if x is the number of successes in a Bernoulli sequence with a fixed success of probability p, then we call that sequence a binomial random variable. Binomial again meaning two possible outcomes. And a binomial random variable will have a binomial distribution. So we always write out these binomial random values as follow, right? So we write x, and then we write that squiggly line, bi for binomial, and then we always write the number of trials first, represented by n, comma, p. And these are two important variables when it comes to working out the binomial distribution. The order doesn't matter in which these events occur, right? Because they're all independent from each other, so the order doesn't matter. And so we use this thing known as combinations or combinatorics, right? Combinatorics, sorry. So combinations, how do we do them? We do them with this thing called a factorial. So n factorial is given by n times n minus 1 times n minus 2 and so on until it equals 1. For example, the factorial of 4 is 4 times 3 times 2 times 1. 0 factorial is equal to 1, so that's why it's not included here. So combinations don't actually care about order, right? So it's shown as NCR, so number of people to choose from possible groups, right? So for example, if I want to choose 3 people from this lecture, how many groups can I choose? I'll let you guys sort of figure this out. Maybe you've done this sort of stuff before. If you haven't seen it before, that's all good. So if you're entirely lost right now, that's fine. I'm going to go through that. So let's look at this. So 10 people touch on when they board a tram and 4 are caught. How many different combinations of people are possible? So we're going to say that the number of people, right, possible are 10, right? And the groups are 4, right? So 4 of these, so I'm choosing 4 from 10. How many ways can I choose 4 from 10? That's what this is asking, right? So you read this as 10 choose 4. So C for choose. So I just chuck it into the equation. So 10 factorial divided by 4 factorial times 10 minus 4 factorial. And so that's just this. Now, if you leave things in factorials, you can cancel them out. So 10 times 9 times 8 times 6 factorial. So then these 6 factorials can cancel out. And so you're left with 10 times 9 times 8 divided by 4 times 3 times 2. So it's always good to cancel out where you can. So the 4 and the 2 are going to cancel out with the 8. And the 3 and the 9 are going to cancel out to make 3. So it's just 10 times 3, which is equal to 30. And so we can put this all together with probability to form the binomial formula, right? Where x tells you the number of successes you have, p is the probability of success, and n is the number of trials. Okay, so this reads basically as number of successes given n number of trials times the probability of successes times the probability of no successes. Right, this here is the number of times, so it's n minus x, right, which is the number of failures. Right, and this only works because each event is independent. So what's happening is the first, for example, in 5, I get 4 successes. So then I have to do the probability of success times 1, times 2, times 3, times 4, right? Success once and twice and 3 and 4, right? Hence they multiply. That makes sense because it's and, right? And I also multiply by the chance of 1 failure. So it's 1 minus p once. Okay? Hopefully that makes sense. Which is why it simplifies to be like 5c4 p to the power 4 times 1 minus p to the power 5 minus 4, right? Let's do a question. So let's say, Doctor Strange found that Iron Man has a 90% chance of dying over all possible timelines. Let's say we take 10 random timelines. What is the probability that Iron Man dies in every timeline? And what is the probability he dies in a half? I'll give you guys some time to think about it. Have a pause maybe. See how you go. In the meantime, I'll work it out. So generally my first step, let me just quickly have some water. My first step generally is to set up my variable, right? And so I'm going to write, the reason I do this, by the way, is so then I have all the values I need in a nice small package, as opposed to a slab of text. The only 2 things I really need, apart from this Iron Man garbage, well, I don't need the Iron Man garbage, sorry. What I do need is the 0.9 from the 90% chance. So the probability of dying is 0.9. That's what we've defined as a success, right? That because we're trying to find when Iron Man dies, right? So the probability of death is success. Sometimes the probability that they give you is not the probability of the success. So you've got to be really careful with that, right? And then we want to take 10 random variables, and so n is equal to 10, okay? So we have x is binomially distributed with n is equal to 10 with probability 0.9. So let's say we want to work out the probability he dies in 10 random timelines. Again, order doesn't matter here. It doesn't matter in what order he dies or in which order of timelines checked he dies. It needs to matter that it happens, out of the 10 times it happens 5. Or, he dies in half, right? That's what we're working out first. So x is equal to 5 out of 10, that's half. This is just 10 choose 5, right? It's the same thing as a factorial, like the combinations. So I subs that into my NCR equation. I'm calling it an NCR equation because it's like this, right? And then I sub everything else into my binomial equation, and I get 0.001 to 3 decimal places. Now, since this didn't really ask for any decimal places, it's probably better to just give it as an exact value. Okay. Now let's go to a new question. We take 10 random timelines. What is the probability that Iron Man dies? Also, I forgot to talk about what is the probability that Iron Man dies in every timeline. In this case, you do probability of x is equal to 10, right? So 10 by 10 times 0.9 to the power 10. And here it's 0.1 times 10 to the power 10 minus 10, which just cancels out, right? Now, if we go back to our formula for NCR, back here, sorry, if I have two of the same number, so if it's got 10 choose 10, well, by common sense, there's only one possible way to choose 10 choose 10, right? I just need to choose all of them. I can show that mathematically by this. So 10 factorial divided by 10 factorial times 10 minus 10 factorial. And that's just equal to 1 because these cancel out. That's equal to 0, and 0 factorial is equal to 1, right? Sorry, I went back a little bit. And so really, this is just equal to x is equal to 10, all dies in all timelines, is just equal to 0.9 to the power 10, which is the same as saying he dies in timeline 1 and dies in timeline 2 and dies in timeline 3 and so on, right? I've just multiplied 0.9 by 10. 0.9 by itself 10 times. Cool. Hopefully that makes sense. Okay, so we take 10 random timelines. What is the probability that Iron Man dies in less than 2 timelines? So again, I want to write out what my variable is, right? And now I've got the probability of x is less than 2, right? This is also the same as the probability of x is less than or equal to 1, because it's a discrete sort of distribution. Remember, binomial is discrete. So keep that in mind, so discrete, right? So the probability of x is less than 1. Which is also just equal to the probability of x is equal to 0 plus x is equal to 1. We can't have less than 0 in this case, right? It doesn't make sense for him to die in -1 timelines. And now I just sub that into my binomial equation, right? And this works out probability of x is equal to 0. And then I can work out probability of x is equal to 1 separately. And then from there, I sum them together, right? And that gives me my wanted value there. It's here, by the way. Okay. What is the probability that he dies in at least 1? So the probability of x is greater than or equal to 1, so at least 1. Again, same thing. So there's two ways to do this question. One is to add everything from 1 to 10, right? But since we know all these outcomes, since it's just a probability distribution must sum to 1, we can just do the complement. So I can do the probability of x is less than 1 and do 1 minus of that, right? So this is just the complement of each other, right? It's the complement. And the probability is x is less than 1 is just equal to the probability that x is equal to 0, right? Because it's discrete. And so that's where I get this from. And I worked out what x is equal to 0 was from the previous slide. And this is basically just 0, right? Which is why we get 1.000 to 4 decimal places. Okay, so the binomial distribution has a different formula for mean and variance. And so this is as follows. And also for the mean, it's just the number of trials times the probability of that trial, which is quite nice, right? It makes sense if you think about flipping a coin as well, right? The probability of flipping a coin is 0.5. Let's say I flip a coin maybe like 5 times, so n is equal to 5. The probability that I get tails is just going to be, probability of 0.5 times 5, right? Half of the times I'm going to get tails. So 2.5 times I should be getting tails. which is kind of iffy, I guess, with a discrete sort of distribution. So that's either it's probably better to just round up to 3. For binomial distributions, the formula for variance is just np times 1 minus p. So the expected variable, or the expected value, times the probability of the complement, more or less, right? Again, remember that the variance is equal to the standard deviation squared. And so if I want to work out standard deviation, right, that's just equal to np times 1 minus p, the square root of that, right? So these are quite important to know. They will get you to calculate this sort of stuff. So try not to get this confused with just normal discrete formulas. It does follow an entirely different rule. So there are 2 main calculator functions. So the binomial probability density function, or PDF, is given, which gives you like a particular x value. So if I've got, the probability of x is equal to 2, that's when I want to use a PDF, right? If you're not sure where this is on your CAS, Google is probably your best bet. I'm not sure what CAS everyone uses. I use the TI Inspire. So if you do use the TI Inspire, it's, go into the menu and then under probability, and if you scroll down, you'll find binomial, I think, and then from binomial you can find binomial PDF. And just pressing that in and filling out the information page that comes up will just give you the value. Binomial CDF, cumulative density function, as it says, is cumulative. It sums up, right? It sums up multiple terms. So it'll generally do things that are like greater than or less than, or greater than and equal to, or less than and equal to. And you don't really have to worry about converting things like x's less than 1 to probability of x is equal to 0. It'll just do it for you, right? So just write it in as the question says, simply because you won't make a mistake doing this conversion. You're not gonna, like, if you do that conversion by hand, you might make a mistake, but it's super unlikely that you make that conversion mistake when you're doing it, just entering into the calculator, because the calculator just calculates it for you. Okay, let's talk a bit about the probabilities of the mean and the variance. So the expectation allows us to work with mean and variance of a random variable without rewriting the distribution, right? So what do I mean by that? So if I have, some new distribution, right, but it's only multiplied, it's like some scalar multiple plus some constant, I can just use the old mean and continue on, right? So sometimes this is a really common question type. They'll like give you some x term, and then they'll say, let's double that x term, right? And then add b to it, or add some value to it. If you want to calculate that out, just sort of use this rule here. With the variance, it's a little bit complicated. The b just disappears, right? And the a comes out the front and gets squared, and it's the same as a squared times the variance of x. So the variance has no horizontal translation. I'll give you guys some time to think about this. Drop your answer in chat, or your guess. Obviously, there's no penalty for getting the wrong answer. It's just a good idea to sort of brainstorm as to why variance could have no horizontal translation. And I'll answer that question on the day. So yeah, just chuck it in chat. If you are rewatching the recording from the day, I'd recommend taking some notes of that. Okay, let's get on to continuous probability. So what is continuous probability, and what's the difference between discrete and continuous probability, right? So a continuous random variable is that one that can take up any real number, right? So it doesn't have to be an integer or a natural number, right? A continuous random variable has some of these properties. So it needs to be greater than 0 for all of x. So keep in mind, I'm now using a function. It's a bit strange, right? But we'll sort of see why a function makes more sense than what we saw earlier. So the probability must be, what this simply says is that the probability must be greater than 0 for all x possibilities, right? Which is just stock standard for probability. The area enclosed by the graph and the x-axis must be equal to 1, right? So that's taking an integral from a to b of f of x minus 0 d of x must be equal to 1. It's more accurate actually to write infinity in both of these. So negative infinity to infinity. So for the full length of that function, the area enclosed must be equal to 1. Okay? And so, that's sort of represented here. But if I want to work out between two particular areas, I need to work out the integral, right? So the probability of x is less than a is also equal to the probability of x is greater than or equal to a. Oh, wait, less than or equal to a, sorry. So here are a couple different variables that are going to be under a continuous that two of them are under a continuous probability, like you guys just saw, and one of them isn't. And I'm going to sort of explain why. Well, obviously with postcodes, you can't have, like decimal. You generally don't have decimal points with postcodes, right? You'd hope. Whereas with metro, time that things can run late by or height, like I mentioned earlier, that's going to be on a spectrum, right? It's going to be on some, continuous scale. So hence those two are continuous, whereas postcodes is not. So we generally represent continuous probability by what's known as a probability density function, or a PDF, right? So when we talk about continuous variables, we refer to them over an interval rather than a particular case, right? So we ask, what's the probability that someone is between 163 and 178, right? Because that includes these point heights, like, 0.9, 0.2, right? So if we want to find 163 to 178, we want to take the integral from 163 to 178, right, of f of x with respect to dx, right, as shown in the slide earlier. Oh, sorry, I should go back. So yeah, when we're doing those calculations, 163, 178, those are going to be our terminals, right? Another thing to note is that you can't find, for a continuous probability function, you can't find a particular case. I'll give you guys maybe a second to think about that. Why could that be true? Type your answer in chat. Why would this be equal to 0? Because it is. Okay. One possible sort of explanation is that if I want to work this out for a probability density function, right, when it's a continuous function, what I'm doing is I'm taking an integral from 163 to 163 in both cases of f of x dx, which is just capital F of 163 minus f of 163, right, which is just equal to 0. Now let's, mathematically that's sound, right? But let's sort of think about it in a realistic sense, right? And I want you guys to type, your thoughts on that into chat rather than just, the thoughts about, why it's mathematically 0, right? So let's think about, like a group or like a sample of, like 100 people. Well, let's just think about the Australian population in general, right? What's the probability that, let's say you put every Australian like person on Australia, let's say you put them in a bag, right? Like let's say you just have an infinitely large bag, you can put them into a bag, and then you reach your hand in and you grab one of them and you pull them out. What's the probability that they're exactly equal to 163 centimeters? Like, what's the probability that their height is exactly 163 centimeters, right? Super low, impossible, right? In that scale, maybe there's one person who's exactly 163 centimeters, but it's out of millions, right? Like too many, right? That's just approximately 0, right? So in both, mathematically, using the sort of calculations we've been taught, and, using sort of sense and logic, we can sort of see why, with continuous probability, it's really hard to find a particular value that's not equal to 0. So your probability, continuous probability questions are always going to be like, what's the probability this population's height is between these two values? What's the probability that, this ball has a speed between these two values, or less than this, or greater than this, right? If they ask you a question like, what's the probability of x is less than 100 you would do an integral from, an upper bound of 100 from negative infinity to an upper bound of 100, right? Why is it okay to use negative infinity? Sorry, that's not a -8. infinity. Why is it okay to use a negative infinity? Because it's likely your probability density function tapers out at the bottom. Maybe it looks a bit like this, right? So from here, which is like about 100, let's say that's 100. And this just keeps going on, and it keeps getting closer to 0, right? Once it's past x is equal to 0 on, the y-axis, it's hit 0, right? But yeah, so if you're doing from negative infinity to 100, you're really only capturing this region, right? Which is fine, which is like perfectly fine. So when you're doing less than, I'd recommend using negative infinity. If you're doing probability of x is greater than 100, I'd recommend using your upper bound as infinity, and my infinity symbols are not it today, and 100, right? So f of x dx, so 100 to infinity, because that's 100 is your lower bound. Okay, hopefully that makes some sense. So we're going to finish off today by talking about the normal distribution. So what is it? What does it mean for something to be normally distributed? It means that the data is, has a fixed mean and it follows a bell curve shape, right? So it's a special type of continuous probability, right? It's the most, common type of continuous probability that you will see, and you've probably seen in your day-to-day. It's these sorts of shapes, right? Where like the center is the mean, okay? And it's generally given a sort of, like with binomial, how we write it with bi. In this case, we write x is distributed with n for normal of mu, comma, sigma squared, or variance, right? Like so. The actual equation for a normal distribution is this. And you will never use this, right? You can maybe have a go chucking it into your calculator. Maybe like, for fun, maybe throw in like mu is equal to 1, sigma is equal to 1, or mu is equal to 0, sigma is equal to 1. That's your standard normal distribution. And maybe, doing it from like integrating it from, 0 to 1, see what you get. Your calculator might chug for a while, but it should spit out a nice value. But yeah, you'll never use that, so don't worry about that too much. Like I said, it follows this really special bell-shaped curve. And what's really nice about this, so this one here is your standard sort of normal distribution. You can see that its mean is centered at 0, so mu is equal to 0, right? And here, this is just the probability, right? You don't need to worry too much about the y-axis, or frequency, sorry, not probability. You don't need to worry too much about the y-axis in continuous functions. Really, what's important is the area under the curve, okay? So we can see here we have standard deviations, right? And each standard deviation captures a certain amount of percentage of the curve, right? So this is something you need to know, right? So with normal distributions, one standard deviation is always going to capture 68% of the curve, right? So 1 st is 68%, right? 2 standard deviations is going to cover 95%, and 3 standard deviations is going to cover 99.7%. So it's totally it's totally reasonable for them to ask you to use these values to approximate things on a normal distribution. So you should know this. Know that standard deviation can either go up or down. So from 0 to 1, right, it captures 34%, and then from -1 to 0, it captures another 34%, which is where you get your 68 from. Same with the 95 and same with the 99.7. So let's try and explain this bell curve, right? So the probability, like I said earlier with continuous probability functions, is bound by the area under a graph over some interval, right? So again, we use that, same formula like we sort of talked about earlier, right? But since that function for a normal distribution is so complicated, it's just done using a calculator function. So you will have a normal PDF function that you can use to do this. With the bell curve, most of your data lies around that mean, right? Like you can see within just one standard deviation, you already capture 68%, right? Within 2, you already capture 95%. So a lot of your data is centered around the mean, right? So the further you go, you can see in these like small pockets here, you've only got 0.15%, right? So tiny bits, right? So the further you go out, the less data you have. And so each line, right, represents, in this plot, right, represents a standard deviation from the mean. So at the mean, you can see it says 0 standard deviations from the mean. At 1, it's +1 from the mean. At 2, it's +2 from the mean, right? So hopefully that makes sense. Sort of already covered this, so I'm going to skip over that. So it's known as the 68, 95, 99.7% rule, and yeah, you do need to know this. So let's have a crack at this. So if the age of students in a particular awesomely spectacular methods lecture, maybe this one, was normally distributed with a mean of 17 and a standard deviation of 0.3, over what range do we expect 68% of the students to lie? Well, so we have a distribution, normal distribution, right? Which is what they've said, normally distributed here. So mean, we said, was 17, and standard deviation is 0.3. So here, again, that represents the variance, so that's just sigma squared. So you can just write 0.3 squared. So using our rule, right, 68% of our data lies within the one standard deviation of the mean, right? And so all you have to do is 17 minus 0.3 and 17 plus 0.3. So your data is going to be between 16.7 and your ages are going to be, with 68% lies, is between 16.7 and 17.3 years old. Okay, so I've mentioned the standard normal before, or the standard normal distribution. I said it has a mu of 0, so mean of 0, standard deviation of 1, right? So we usually represent it with a z instead of an x, right? Just so we don't get confused. So z always generally represents the standard normal curve, right? So it's got a mu of 1, mu of 0. It has a sigma squared, or variance of 1, and a standard deviation of 1. Sorry, so scribble that. Standard deviation of 1. Okay, so we can get any normal. The really neat part about a normal distribution is that we can get any normal distribution and move it to a standard normal distribution. How do we do that? We use this equation, right? So any normal variable or standard normal variable is equal to the normal variable minus the mean of that normal variable. So these means and standard deviations are different from 0 and 1, right? So it'll be whatever it is for the distribution. So the standardized value tells us the number of standard deviations the x value lies from the mean, right? So this can be particularly useful for using that 68, 99.7 rule, right? So Vika claims that the VCE scores are calculated this way, though I'm not 100% sure on that. I mean, it's likely that it is. What they do is they do try to put it on a normal distribution, so you have study scores represented that way with the mean at 30. But I'm not 100% sure. I'm not an expert on how they do that. Let's go through an example using this formula. So let's say we have the same sort of distribution as before, mean of 17 with a variance of 0.3 squared. So how many standard deviations of the mean from the mean is the age 17.6? Okay, so let's try to work that out. So we just chuck that into our equation. So 17.6 minus 17 divided by 0.3, that's just equal to 17.6 minus 17 is equal to 0.6. 0.6 by 0.3 is just equal to 2. And if we try work that out with 16.7 as well, we'll see that we get -1, right? But that just means we've gone, instead of going above the mean, we've just gone below the mean, right? So at the end of the day, that's still one standard deviation away from the mean, okay? And now they want us to approximate this. They want us to approximate 16.7, the probability that the age is 16.7 to 17.6. So how do we do that? So first, I'm going to work out this, and that tells me the probability that it's one standard deviation below, right? So if I go back to, yeah, so if we go back to, I might go one more back to the bigger image. Sorry about that. So if we go back to this one, right, we can see that one standard deviation is 68. And so I've gone here, right? So I've gone here, and now I want to go to here, right? So that's what we're doing. That's the calculation more or less, right? So I've gone, the probability captured here is 0.68 divided by 2. And what's captured in here is going to be 0.34 plus 13.135, right? Which is more or less what we've done when we go to our question. Sorry about going so far back. I just thought it'd be good to show the image. So that's where that comes from, and this is also where this comes from. It's just like, calculating the upper half of that. And so when we sum them together, we get the probability is equal to 0.815. Just to continue with the example, this is just what I just showed. So all we're doing is we're working out this, right, which is just equal to 0.68 by 2. And then we're also working what this is, which is just equal to 0.95 by 2. So this rule is approximate, right? So, it's not exactly 68%, but it's good enough, right, for that determination. But, for exam 1, that's good enough because they only want approximates. But, to actually work out your exact values, you're going to have to use your calculator. And like I said earlier, you want to be using the normal CDF and not the PDF, just this CDF function. So let's have a crack at this question here. So find the exact percentage of the amount of data that lies within one standard deviation of the mean. So we just enter our values on the CAS. You can actually TI Inspire anyways. You can just type in norm CDF, or you can also find it under menu probability. And so you just enter the various variables like this, right? So this is your lower and upper bound. So this is your lower bound, and this is your upper bound. And here, this is your mean, and this is your standard deviation. So when you do that, this is the exact value. It's about 68%, but this is good enough. All right, let's have a crack at this one here as well. So the height of a giraffe is normally distributed with a mean of 4.3 meters and a variance of 0.05. Find the probability that the height is greater than 4.5. Again, I'd like to write out my variables. And the lower bound, right, so it's just greater than 4.5. The upper bound is infinity. So you can just enter that in to your calculator, and you get 0.186. Now this one here is conditional, right? So the probability that the height of a giraffe is greater than 4.5, given that it's 4.2, right? So that numerator is the probability of x is greater than 4.5, intersecting with the probability that x is greater than 4.2, right? And the intersection between these two regions, right, is probability of x is greater than 4.5, which is why that's only present on the numerator. So entering that into our calculator, we'll get this. Okay, so Toby is delivering 7 giraffes to the Melbourne Zoo. What is the probability that less than 4 giraffes, that less than 4 of his giraffes are less than 4.35 meters tall? So again, we just create our variable. So the probability that x is less than 4.35 is what we want to work out. So lower bound negative infinity, upper bound 4.35. So we enter it all in, we get 0.588. Now that's not the entire question, right? We want less than 4 giraffes, right, out of 7. So now we can do a success failure sort of definition. So now we're applying a binomial distribution to a normal distribution. And so, we can use this as our fixed probability, sub it in, use a binomial distribution. Again, I'm going to be using binomial CDF. And there we go. All right, let's talk a bit about the inverse normal. So the inverse normal is, the inverse of a normal CDF, right? So whereas the normal CDF gives us, the probability, the inverse normal gives us the upper bound, assuming that we're taking the lower bound is negative. So it always finds the areas left to a value, okay? So the total time people spend scrolling Netflix is normally distributed with a mean of 120 hours and standard deviation of 10 hours. And so again, I always like to write out my variable like this. It is found out that 10% of people have wasted their life, so this is 0.1. A person has wasted their life if they spend more than 8 hours scrolling Netflix. Find A. So we can use probability of x is greater than A is equal to 0.1. So we need to change it so that it's on the left, right? So x is less than A. We're using that complement rule. I'm just doing 1 minus 0.1, which gives me 0.9. And then I can chuck that into my calculator. So inverse norm is a function under probability as well. And that gives you 132.816. And in some cases, we're not given, standard deviation or the mean. However, we can determine these using a normal inverse function, right? Or inverse normal. So we've got from earlier, z is equal to x minus mu over sigma. And so what we can do is we can standardize a function. So that means, even though it's like some different normal distribution, we can bring it back to the standard normal distribution using this equation here, right? Which, is zn01. So here's an example. So x is normally distributed with a mean mu and a standard deviation sigma. It is known that 35% of the data lies under x is equal to 6, and 45% lies above x is equal to 10. And now they want us to find mu and sigma. So I'll let you guys have a crack, and while we work it out. So the probability that x is less than 6 is equal to 0.35, which is given in the question. Probability of x is greater than 10 is equal to 0.45, which is also given in the question. So I can use my z is equal to x minus mu over sigma from earlier to sort of standardize it to the standard normal distribution, right? Then I can use inverse normal because the area known under the standard normal distribution is like a known quantity. So inverse normal can handle it reasonably well. And so I work out what the area is, sub that into my, so I work out what z is more or less, right? And then from there, I can use simultaneous equations to solve for mu and sigma. Here's a couple of exam questions that I won't go through just for the sake of time, but you guys are more than, the solutions are there, and it's always a good idea to have go through those. So that brings us to the end of today. So in summary, we sort of just covered, a brief understanding of integration, and we went into a lot about probability. Now, I would like to remind everyone that that's not, everything. What is, method? What at the end of the day, methods is primarily about the problem solving. So although the content is all covered here, it is really important to go ahead and practice these concepts and try to get your hands on any sorts of questions you guys can. But yeah, hopefully you guys enjoyed today. If you have any questions, chuck them in chat. I'm more than happy to answer them. And if I maybe miss your question or you're watching a recording, or like recording after this session has aired, feel free to shoot me an email from the email at the start. So it's just aj@tutesmart.com, and I'll get back to you as soon as possible. So hopefully you guys enjoyed today, and I'll good luck with your rest of methods 3 and 4. But yeah, hey.